Okay. In the previous segment, we introduced the notion of mass density. We saw what it means. We made the observation that in our treatment of continuum mechanics, in our elementary treatment of continuum mechanics, we are going to insist that the mass density remain continuous regardless of the deformation. And then, toward the end of that segment, we worked our way to noting the relation between the mass density in the reference configuration and that in the current configuration. Okay, so let me just pick up the thread there. Okay, so we have mass density in omega naught and omega sub t. Okay, and that relation is the following: rho little x comma time equals rho 0 capital X j inverse x comma time. All right. J, observe the J is the determinant of F. Let's just recall that J is the determinant of F, and therefore it's a scalar. Right. So when I say the inverse of J, I just mean 1 over J. Okay. All right. Now remember that we started this unit by saying that we were going to talk about the balance of mass. Okay. So we can ask ourselves the question, how do these mass densities change with respect to time? Okay. So the idea of the balance of mass in continuum mechanics comes from this idea. Balance of mass is a question of the rate of change of mass density. Okay? And the reason I wrote it out in words is because I do not want to prejudice the discussion by introducing already a particular type of time derivative or the other. Okay? All right. So let's ask this question. Okay. So let's ask ourselves, first of all, let's now ask this question in omega naught. All right? So this question then becomes, if you're going to talk about things in omega naught, we use something that's parametrized with respect to position in omega naught. And so the question we are asking is the following. We're asking, what is this quantity? Okay? This is actually a trivial question, right? Because really we are saying, what is the time rate of an object that has no time dependence, right? So obviously this is 0. Okay? Pretty obvious. May seem a little trivial, but it's not really that trivial. What we're saying is that, okay, we have the body here in its reference configuration, right? We have the body in its reference configuration, and it's going to deform, right? Perhaps as a function of time, right? It's going to deform. The question we are asking is mathematically, well, as this body is deforming, what is happening to that function rho 0, which described for us the distribution of mass before deformation? Well, it doesn't matter what's happening here, that function doesn't change, right? Even physically, right? So we do have this notion, right? That nothing is happening to the body such that if you were to go back to the reference configuration, you would find that because of this deformation, all the way back in the reference configuration, also the density had changed. Okay, we're saying that is not allowed, right? We're saying that we're not considering any kind of physical process by which the deformation of this process does something fundamental to the mass, such that the mass density, that maybe the mass is reorganized or something, so that even when you take off the deformation, right, take the inverse of the phi map, right, take the inverse of the motion map, go back to the reference configuration, right? We're saying that the mass density still is the same. Okay? So even though mathematically it looks trivial, physically it's not that trivial a notion, because you may imagine that supposing the deformation were to induce some sort of chemical processes which were to change the distribution of mass and all of that, things could be different if you were to map back to the reference configuration after the deformation, right? Okay, so we're saying that none of that happens. Okay? So this is our basic statement of the balance of mass. Okay? So this is the balance of mass, or alternately, what it tells us is that mass is being conserved in this process, right? We are saying that in the processes of deformation that we have here, right? In the processes of deformation that we have here, we are not adding or taking away mass from the body. Okay? There are processes when that is no longer the case, right? And we may see that toward the end of the series of lectures. But for now, we're saying that we indeed have conservation of mass, right? So we have conservation of mass. Okay? And since I said all that, I'm going to include a remark here that mass may not be conserved if certain processes of transport and reaction are allowed. Okay? So mass may not be conserved if certain processes of transport and reaction are considered. Okay? So we are not considering these processes of transport and reaction, at least not yet. So this is our statement of conservation of mass, and because rho 0 is defined in capital X, it's pretty clear what this means. Now, we can, however, ask a different question. We can say, all right, but we've very conveniently written this in terms of our reference mass density. What does this say, however, about the current mass density or the mass density in the deformed configuration? Okay? So we can ask now, what about rho little x and time? Now, the reason for asking this question, what about the rate of change of the density in the deformed configuration, is a relevant one because of the following idea. We have this, right? We have the body in its reference configuration. And in the context of solid mechanics, because we have this Lagrangian description where we tend to follow material points, right? Look, you're following the material points, right? In that setting, we know that we can always map back to the reference configuration, okay? And so we can always pose this question of the balance of mass in terms of the reference density in the case of a solid, right? This is natural. The Lagrangian description gives us this ability, okay? Too bad if you're doing fluids. Okay, so now imagine, of course, I've got a contained fluid here, but imagine that this was a continuous tube, right? And that this green fluid was really fluid coming in from the, in my case, from the right-hand side of this room, flowing into this bottle, going through this window and exiting out of this side if I were to open it out, right? It'd create a mess here, so I won't do that, okay? Now now we have a problem here because in the context of a fluid flow, we don't have access to the reference configuration. If this were a wind tunnel, right, we don't have the ability to go back to the reservoir, or sometimes there isn't even a reservoir, right? The reservoir is all of the outside because a wind tunnel is often set up with this big fan that blows in, that sucks in air from the outside. The notion of a reference configuration is just not available to us. It exists mathematically, but we just don't have access to it because it's much too complicated to get at. So we need something else. We still need to be able to talk about the balance of mass in the context of this fluid, where the only thing we have is the following. The only thing we have is this little window into the fluid. Right? That's all we have, and we need to be able to talk about the balance of mass when this is all we're seeing. Okay, we have access to quantities here. We know we have the velocity, right? From these conditions that we wrote out, we know that we have this notion of density, mass density in this configuration. In the context of a fluid, we would directly measure rho of little x and t. We would directly measure what I've written up on the slide here in this little window. Okay? How do we pose the question then? Okay? And for that, we turn back to this relation. Okay, so this is a question, so let me make it a question. Okay, so what we do is use this relation. I'm going to rewrite the relation that we had in the previous slide in this form. Okay, turned it around, essentially took j to the other side. Okay, so we have this, and then we say, we know that this partial time derivative okay, all right, and here what are we doing? We're holding capital X fixed, right? Right, it's obvious on the left-hand side, but I'm stating it nevertheless. Okay. This is then the derivative with respect to little t, right, of rho little x and time, j capital X and time, okay, where we know that little x is composed by the motion from capital X, and I will make it very clear here that we have x equals phi of capital X comma time, and this quantity is fixed, right? That is the kind of derivative we are taking, okay? All right. Now, just applying the product rule, we know that this is derivative with respect to little t of rho x comma t, but now we're talking of taking what kind of a derivative here of rho? It's not just our old-fashioned partial time derivative. It is the special time derivative we saw a few segments or about 1 unit ago. It is that total or material time derivative, right? So we have this, but then we need to remember that x is phi of capital X and time, and what we're doing here is holding this quantity fixed, right? We take that derivative, j comes along for the ride, okay, and we have rho of x comma t. This is now just a simple partial time derivative because j is conveniently parameterized for us in terms of capital X and time, and capital X is what we're holding fixed there, okay? X fix. Okay? All right. We know how this works out. We know how to compute the material time derivative of a quantity that has this dependence upon the spatial position, right? Okay? So, let me just say here, recall material time derivative okay, to do this, to do that step. Okay? You could go back and look at your notes from a few segments ago. I won't rederive the entire process here of writing out this material time derivative. Sorry, I should write material time derivative here. Okay, I won't rederive that entire result, but I will essentially use it. Okay, so again we have partial with respect to time of rho 0, x comma t on the left hand side. Okay, on the right hand side we have the following. Okay, that material time derivative does involve the partial time derivative, but it is not all. Now I'm going to suppress the use of argument. Well, okay, no, I will write arguments. Let's say just this time I'm going to write them. Okay, so this is the real partial time derivative. Okay, plus we have the gradient of rho. Okay, the spatial gradient of rho. Okay, parameterized by little x and t. Okay, rho is a scalar. Its spatial gradient is a vector dotted with v, the spatial velocity, x comma t. Okay, all of this multiplying j, capital X comma t, plus rho little x comma time j dot. The last partial time derivative on j is just j dot, because j, the other argument of j is capital X, which is fixed, of course. Okay, so we have this. Let me just write it out in coordinate notation. The only place we need coordinate notation is for this bit involving the convective derivative. Okay, that's a dot product, so I can directly write it out using coordinate notation. It is basically, okay, partial of rho with respect to x little I vi. Okay, I've suppressed the arguments in that. Okay, all right. Now this is all very clear. The only thing we need to do is to do a little more work on writing j dot. Okay, all right. Now consider j dot. Okay, x comma time. All right. Now this is derivative with respect to time of the determinant of f. Right, and the determinant of f has this dependence upon capital X in time. Using the chain rule, this is derivative of this determinant function, okay, derivative with respect to f of that function, contracted with partial of f with respect to time. F is a tensor. Okay, just to make clear what is happening there in that last step, I'm going to write it in coordinate notation. Okay, it is derivative with respect to f little I capital I of the determinant function of f. Okay, remember the determinant function of f is a scalar, right? So we are talking of differentiating a scalar with respect to a tensor. Okay, contracted with the time derivative of f little I capital I, which is just f dot little I capital I. Okay, that's what we want to do. Now the tricky part is that derivative of the determinant of f. Okay, so let's write it out, recalling what we have for determinant of f. Now, determinant of f, derivative of the determinant of f with respect to f I is equal to, okay, we're going to write out the determinant using our permutation symbol, okay? And the way that worked out is that we have, okay, I'm going to use epsilon, little a, little b, little c, epsilon, capital A, capital B, capital C, F, little a, F, little b, capital B, F, little c, capital C, and we have 1/6 of all of this. Okay? Sorry, it's the derivative of this with respect to F, little I, capital I. Okay? This is what we're trying to compute. Now, it's easy to do this by observing that, well, these are all, the permutation symbols, epsilon here, are just constant, right? Just numbers. So it's really the derivative of f with respect to itself that we're talking of doing here. Okay? Now, because those are components of f in the numerator and, well, not in the numerator, but in this derivative, that's not really the numerator and denominator when we talk about a derivative, but we have those components. We know that when we take this derivative, we essentially get our Kronecker delta. Okay? So, this is 1/6 epsilon little a b c, epsilon uppercase a b c. We get now, all right, now we get terms of the form delta a little I, delta capital A, capital I, F, little b, capital B, F, little c, capital C, plus F, A, delta little b, I, delta capital B, I, F, little c, capital C, plus F, little a, capital A, F, little b, capital B, delta little c, I, delta capital C, capital I. Okay? All right? Now, this has a certain effect, which is that if you look at this, what it does is that, let's look at the first term. Observe, I'll show you what happens with one term here, and essentially what's happening is that this Kronecker delta is going to act on that A, okay, turn it into an I, and this A is going to contract out with that one and turn that epsilon capital A into an epsilon capital I. Okay? And the same thing will happen for the subsequent terms. All right? For instance, out here, it is going to, this B here is going to act upon that B and so on. Okay? Turning that into epsilon AI little c. Okay, so work it out, just apply the Kronecker delta and all those indices, and what you will end up with on the right-hand side is a different function of f. All right? Okay, so let me just tell you what the step is here. Apply Kronecker delta to permutation symbol indices. Okay, by that what I mean is things like delta a little I, delta A capital I, epsilon A B C, epsilon capital A, B, C. You would reduce as as epsilon little I, B, C, epsilon capital I, B, C, and so on. Okay? When you do all of this, what you see is, what you observe is that the derivative of determinant of F with respect to little f I, you will find that it gives you the components of a different function of f. It is the cofactor matrix of f. Okay? The cofactor matrix is a different matrix of f. Okay? And you get that cofactor matrices I component. Okay? So, do you recall what the cofactor matrix is? It is involved in the calculation of the determinant, unsurprisingly. Okay, it turns out that the cofactor matrix of F is the following sort of thing. Okay, so recall. If you write out F as in matrix form, right? So it's F11, F12, 1, 3, 2, 1, 2, 2, 2, 3, F 3, 1, 3, 2, F 3, 3, right? That is F written out in matrix form. Now, the 1, 1 component of the cofactor of F is what you may call, using your linear algebra notation or your high school notation of determinant, it is the determinant of that submatrix.